Good morning, dear students. Today we will discuss about the GPS system, that is the Global Positioning System, GPS. So in this topic, we will discuss about the GPS function and terminology and GPS application in Nrcs and Garmin GPS 76 for data collections. So first of all, what is GPS? GPS is a positioning system based on a network of satellites that continuously transmit coded information. The information transmitted from the satellite can be interpreted by receivers to precisely identify locations on Earth by measuring distance from the satellites. GPS is funded by and controlled by the US Department of Defense. The system is called Navistar. So precisely identify location on Earth by measuring distance from the satellite. Navistar navigational satellite timing and ranging. So that is the Navistar. So there are three components to GPS: space segments, the satellite orbiting the Earth and transmitting timing and ranging message, and second, control segments monitor the Earth health and position of the satellite in the space segment and transmits correction information back up to the satellite. And third one is user segments. So in user segment, the handheld or other receivers used to interpret the message broadcast from the satellite. So there are three components to GPS. The nominal GPS operation constellations consist of roughly 24 satellites. Each satellite has a number on your GPS screen. Newer satellites have been sent up to replace older ones, and the GPS signal communicates information about the precise position of the satellite and the precise time of the signal. So each satellite orbits the Earth in about 24 hours. The satellite orbits repeats roughly the same ground track each day. Learn to identify the time of day when satellite coverage is best in your area and plan your field work accordingly. So 2D and 3D positioning of satellite. Since B exists in 3 dimensions, theoretically we needed to get our distance from 3 satellites. The scenario above is theoretical because it supposes that we know exactly how far we are from the satellite. In order to get our GPS clock in sync with the satellite clocks, we need to get data from a 4th satellite to calculate the time offset and set up GPS clock to near perfect system time. Bottom lines, so you need at least 3 satellites to get a 2-dimensional positions and 4 satellites to get a 3-dimensional position or 3D position. So that are the 2D and 3D position of a satellite. source of error that decrease the accuracy of your GPS readings. Number and geometry of satellite visible, signal multipath, orbital and satellite clock errors, ionosphere and troposphere delays, receiver clock errors. Hence, GPS position is not perfect. Some errors you have some control over. As a GPS user, you have some control over the first type of error. So you can wait for the satellite to move into better geometry or plan your data collection for a good time of day. You cannot control multipath error. What do need to recognize when it may occur and pay close attention to the measurements that you are taking. Orbital and satellite clock errors as well as atmospheric delay are invisible to you. What you can avoid them by using differential corrections. There is nothing that you can do about your receiver clock errors. GPS receivers will generally report an estimate of the accuracy of the position being reported by the unit at the time. Next, DGPS, Differential Global Positioning System. In DGPS, improve the accuracy and integrity of standard GPS. DGPS work by placing a GPS receiver at a known location that is called a reference station. The reference station knows its exact location and therefore can calculate the difference between the GPS derived positions and the true positions. The reference station calculate the errors in the GPS signal by comparing its known position to the position derived from the satellite signals. The stations actually calculate the differences between measure and actual range for each of the satellite visible from that stations. This calculated difference is called the differential corrections for that satellite. In real-time DGPS, the correction signals are broadcast from the reference station and used immediately by the roving GPS to correct the position data being collected. There are two main sources of real-time DGPS that USDA uses. The Coast Guard operates a network of reference stations known as the Coast Guard Maritime Differential GPS Service, as well as the developing nationwide DGPS service. The type of frequency that the ND-GPS uses is ground following, meaning that it will not be blocked by most terrain features in its operating range. This means that the GPS users does not need to have a clear line of sight to the DGPS transmitter. GPS users can use these signals if they have specialized receivers like the MBX3 that is included in the USDA GPS configurations. Now in nationwide differential global positioning system NDPGS. So this is the structure of NDGPS. in which a mobile GPS unit and GPS signals and a Coast Guard base stations and differential transmitters from the known position differential correction signal sent in real time. Next, one wide area augmentation system, WAAS. So WAS is a DGPS system implemented by the Federal Aviation Administration and designed primarily for aviation users. The system uses 25 ground reference stations to generate a nationwide correction message. This message is then uploaded to two geosynchronous satellites. The WAS satellite then beam the correction message back to GPS users on L1 frequency, the same frequency that the GPS signal is broadcast on. The target accuracy of this system is 7 meters horizontal and vertical. Testing has found it to be in the 3 to 5 meter range. The target accuracy of this system is 7 meters horizontal and vertical. Testing has found it to be in 3 to 5 meter range. WAS has some serious limitations for users on the ground because the L1 frequency is light of sight, meaning that it can be blocked by terrain, buildings, etc. So this is the wide area augmentation system in which a system connects GPS satellites and also AWA satellites. GPS are not addressed by DGPS. So poor satellite geometry, poor satellite visibility, and multipath interference. So DGPS can eliminate some errors that were discussed in the last slide, but not all of them. Satellites that are bunched in the sky will give a less accurate position than if those satellites were more evenly distributed in the sky. If the satellites are hidden by tree, buildings, etc., then they cannot be used to determine positions. As you gain experience, you will get an idea of where satellites are in the sky at different times of the day. This will help you to plan when to get GPS data in difficult areas. The signal can be bounced around by buildings and other flat refractive surfaces. This can cause some errors because a bouncing signals will take longer to get to your and will therefore tell you that the satellite is further away than it really is. This is called multipath interference, and you just need to be aware that it exists. So accuracy vary by type of GPS unit. Standard GPS 15 meter horizontal, ND GPS 5 meter horizontal, and WAAS, that is the 3 meter horizontal in tests. Next, application of GPS in NRCS. So there are some applications. Determine three-dimensional positions, measure length, distance, measure area, navigations, and GPS mappings. So these are some GPS application in NRCS. Second application, GPS allow the users to obtain, record, and manipulate precise position on the face of the earth. This basic functionality can be used to accomplish the four tasks listed in the previous screen. Determining positions means that you obtain their geographic coordinates, lengths, and area can be measured if endpoints of a line or the corners of a field are obtained with GPS. If you know the coordinates of your destination, then the GPS can show you the distance and direction to that point. So GPS position measured relies on very precise time measurement. Because of that, the general GPS use can tell time with near atomic clock, accuracy. The key function of GS to locate your position on the earth. So there is a location, latitude and longitude, and GPS allow us to obtain, record and manipulate position on the earth. A waypoint gives us to coordinates to a single point locations. Waypoints and tracks give us a digital record in the form of a geospatial layer that we can print to a map. Example, plant, practice, structure, resource layers. So GIS tool allow us to discern relationship and measures distance between points. So GPS also can be used to measure distance. So collected automatically by the unit. For example, the GPS, as you walk the perimeters of a field, the collection garments also has a automated mode that takes into accounts length of a track is calculated as the cumulative. So the GPS can be used to measure area just like length area can be measured using points or tracks. Points can be used to define the area of regular shape area that have well-defined corners. A shape with curving edge like a circular field or field bounded by a meandering stream will be harder to define using points that you determine in the field. Tracks are very good at capturing curving lines as you travel around those edges. The downside is that a track will follow your every move. So here navigation with GPS. So in this diagram, route between 2 points and straight line between 2 points. So here a starting point and second is finish point. So that is the relation between navigation with GPS. Routes. A routes is an ordered set of waypoints that represents the path between two locations. The solid line on the slide shows an example of the straight line between the points labeled start and finish. A route allows you to set an intermediate waypoint on your path from A to B that take into account terrain, roads, or other relevant factors. The GPS will report the length of the entire route as well as the length of each of the segments between waypoints. GPS mapping. In GPS mapping, GPS data can be used to map point, line, and area features. Examples of these features are points, grain bins, utility poles, range monitoring sites, cultural resource area, lines, roads, trail, streams, pipelines, area, fields, wetlands, points in general, and on the GPS units that USDA is acquiring, there is a method to attribute data that you collect in the field. That means that you can give unique symbols and names to the data that you collect so that you can interpret it back in the office. For example, you will be able to distinguish between points collected for a field boundary and those collected to map a grain bin. That is the GPS mapping diagram. Given here, the data collected using GPS can be used to make map of natural resources, physical infrastructure, or any other geographic features. In the slide, the field is an area defined by a four corners points. The road is a line. The lake edge and area defined by a series of points in this GPS mapping diagrams. Now next one, data collection, Garmin GPS map 76. So now required accuracy levels in this system. Use the Dgps beacon to achieve greatest accuracy. Dgps beacons receivers accuracy should be less than or equal to 10 feet. Used for certifying conservation practice. Standalone GPS accuracy should be less than or equal to 20 feet. Users for basic conservation planning, resource inventories, navigations. So that is the layout and button function of the Garmin GPS Map 76. So in this button functions, there is a screen, enter, menu, page, zoom, antenna, zoom out, navigation, power, and Q. These are some functions in Garmin GPS Map 76. So this is the back of the units. So in the back of unit, antenna, cable port, battery compartment, and power data port. Turning on the map 76. So this is the turn on the GPS by pressing and holding the power key. Move through the introductory screen by passing the page key. Setting the map 76 to simulator mode. So you will want to set the map 76 to simulator mode anytime you have the GPS unit powered up inside. This saves battery by not powering the antenna. It also prevents you from getting message telling you that the unit cannot see any satellites. The page and quit key are used to navigate between the pages. So pages on the map 76. GPS information page. That is the GPS information page. And that is the menu, main menu. Interface setups, standalone GPS, backpack, Dgps. Backpack Dgps beacon receivers set the beacon feed to user and then set the frequency and bit rate for the ND-GPS station that you want to use. This is often more effective and predictable than the scan setting. Baud rate setting is a parameter of the communication between GPS and the beacon receivers and cannot be adjusted by the user on this screen. Accuracy. So make a waypoint. A waypoint is the coordinate definition of a position stored on the GPS. To make a waypoint, press and hold the enter key, also called the mark key, until the waypoint dialog box appears on your screen. Use the broker's key to highlight the name field located on the top right of the dialog box. Press enter to begin editing the waypoint name. Waypoint name can be up to 10 characters long. The characters for each field are selected one at a time using up and down on broker key. Press enter the accept a name for the point. So waypoint are automatically saved when you press the mark button. Pressing the quit button before the waypoint information is edited will prevent the waypoint from staying in the memory. Otherwise, if you find that you have created a waypoint that you do not want, select the delete button on the waypoint screen and press enter the GPS until it will ask you for a confirmation before it delete the waypoint. Using the average functions, the averaging functions can be used to reduce the inaccuracy of waypoint. To use average, start marking a point like you would normally before naming the point or accepting it. Press the menu key, press enter to accept average locations. So once the accuracy has stabilized, press enter to return to the waypoint page, highlights OK and press enter to save the waypoint. We have three components in GPS. So first one is space segment, second one is user segments, and third one is control segment. So in this GPS components, we have a antenna and a satellite and the users. So space segment, we have a satellites. The satellite orbiting the Earth and transmitting timing and ranging message, and also in user segments, the handheld or other receivers used to interpret the message broadcast from the satellites. That is the interpreted message broadcast by the satellites. And next one is control segments. That is the third component of GPS. And control segments monitors the health and position of the satellite in the space segment and transmit corrections information back to the satellite. So this is the transmitting between Earth station to satellite and satellite to Earth stations. Next, GPS constellations. The nominal GPS operational constellation consists of roughly 24 satellites. Each satellite has a number on your GPS screen. Newer satellites have been sent up to replace older ones. The GPS signal communicate information about the precise positions of the satellite and the precise time of the signals. So each satellite orbit the Earth in about 12 hours. The satellite orbital repeat roughly the same ground track each day. Learn to identify the time of day when satellite coverage is best in your area and plan your field work accordingly. So there are multi-choice questions for this topics. So question first, what does GPS stand for? Option A, going place sometimes. Second, global positioning system. Third, government positioning satellite. And fourth, global positioning satellite. So correct answer of the GPS global positioning systems. That is the global positioning system. So correct answer is in this question is B, and next questions, what kind of information does a GPS satellite transmit to a GPS receiver? The orbital information for all the other GPS satellites in the fleet, the time the measure was sent, all of these, the location of the satellite. So airplane and boat pilots use the GPS for the navigation. Airplane and boat pilots use GPS for the purpose of navigations. So GPS was invented in 1970. So invented GPS in 1970. So the smallest GPS unit is the one so you can wear on wrist. That is the smallest GPS unit. So smallest GPS unit is the wrist you can wear it